Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in Chapter 2, part of this playlist that I'm calling Discrete Random Variables. And today's topic is random variables and probability density functions. Now, the first minute and a half of what in this video is so important and so overlooked when talking about random variables. Consider an experiment for which the sample space denoted by S, a real valued function that is defined on the space S, is a random variable. In other words, in a particular experiment, a random variable X would be some function that assigns a real number, X, which is a function of the element of S, to each possible outcome S. Okay, so here's a quick example. Consider an experiment in which a coin is tossed 10 times. Let the random variable X be the number of heads observed in the 10 tosses. So for each possible sequence S in the sample space, consisting of 10 heads and 10 tails, this random variable would assign a number X of S equal to the number of heads in the sequence. So thus, if S is the sequence head, head, tail, 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 head, tail, 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 head, then X of S would equal 4. Okay, so that is so overlooked that the random variable is actually a function of the sample space. And the sample space is not always a number. In this case, it's just a sequence of heads and tails. So the set function that we define is X, where it is the number of heads observed in those 10 tosses. It could have been, X is the number of tails observed in that 10 tosses. So this different functions of the same element produce different numbers. Okay, but this is probably the last I'll mention this, and we'll just go with the generic definition that random variables assume values by chance. Okay, so the definition of a discrete random variable, a random variable X is discrete if it can only assume at most finite or countably infinite number of possible values. For example, X in X1, X2 up to Xk. There's only a finite number of elements here. Or X is an element of this countably infinite set. So X1, X2, all the way da da da. And countably infinite means that it can be mapped to the integers. So X1, X2, all the, those are integers and you can count them. A discrete definition of discrete density is let X be a discrete random variable. The function f given by f of x, which is equal to the probability that x is equal to some value, little x. For x is real, called the density function for the random variable x. Now, some of you will say, shouldn't that be probability mass function or probability function? Those are also okay, but it's also okay to say discrete density function. So there's just different ways to say it. Now, a quick R illustration of a discrete density. We're not going to go over the R code. I'll paste it in the comments though. But this could be an example of a discrete density function. So it takes on the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the height of this bar is the probability that it assumes that value. So the probability that it assumes a 2 is, a little less than 0.1. Probability that assumes a 4 is 0.25-ish, and that's it. So necessary and sufficient conditions for a function to be a discrete density is that the density function has to be non-negative, and that's for all possible x's, and they have to sum to 1 for all x's. So you take the values, add them up, it equals 1. And if we look at this previous example in the plot, these are the values that it assumes. And in the code, I summed them. So f is the height of these values. And if you sum them, it equals 1. So this is a probability density function. The probability of an event, so let x be a discrete random variable. Let a be a subset of the real number line. Let this notation, so P of X in A, denote the probability that the value of X will be, will belong to the subset A. So to calculate that probability, you just add up the density function values for all the X that are in that set function or the event A, right? And that's it. That's the probability. A cumulative distribution function, let X be a discrete random variable with density F. The cumulative distribution function for X, denoted by capital F, is defined as this. F of X is equal to the probability that a random variable is less than or equal to that value X, which in the discrete case is the sum of our density function evaluated at all X less than or equal to little x. You just add them up. So let's go through some examples here. So roll one die. Let X be the number observed on the roll. Note that X is a discrete random variable with density F of X equal to 1/6. The cumulative distribution function for X is F of X is equal to X over 6. And let's look at that. So the values that X can assume are 1, 2, 3, 4, 5, or 6. The density function deals with the probability of observing each of those values. And here it's just constant, which won't be the case in later videos in this playlist. But F of 1 is 1/6. F of 5 is 1/6, right? Those are the individual probabilities of observing that value. Now, capital F is a cumulative. So it's the probability of being at that value or less. So F of 3 is the probability that we are 1, 2, or 3, the less than or equal to 3, which is 3/6. So the density function F of 1, F of 2, F of 6 is equal to 1/6. The cumulative distribution function F of X is, in this case, is X over 6. So F of 3, which is probably the X less than or equal to 3, is 3/6, right? Just add up the values. F of 5 is the probability that X is less than or equal to 5. And in the discrete case, that's the same as the probability that X is strictly less than 6, which is just 5/6. F of 0 is 0, right? So we haven't accumulated anything prior to 1. So anything less than 1 is 0. So F of 0 is, and F of 7 is 1. So anything greater than 6, meaning we've accumulated everything. So the probability is 1. Let the event A1 be 2, 5. Then the probability that X is in A1 is 1/6 plus 1/6, which is 1/3. The probability, let the event A2 be 3, 4, and 5. So that's the probability that X is between, greater or equal to 3 and less than or equal to 5, right? Which means you just add up those probabilities. So we know that it's 3/6. But another way to think about this is the probability that X is less than or equal to 5. So that's 5, 4, 3, 2, or 1. But if we subtract off the probability that X is less than or equal to 2, right? Then we're left with the correct probability. But this is F of 5 minus F of 2, which is 5/6 minus 2/6, which is 3/6, which we knew was the correct probability. Now in our illustration of discrete density is, let's let X take on the values 2 to 8, but increments of 2. So that's -2, 0, 2, 4, 6, 8. And we're going to set each probability equal to 1/6. And I'll create a table in just a second. So, let me make it bigger. I always tell myself I'm going to do that. So then we also create a cumulative sum of the probabilities. So that's our CDF, our cumulative distribution function of X. Now I want to put this in a nice table to display. So I row bind them. So I just create rows of each of the things I've created. I also want to create some labels. So I give the dimensions of our new matrix labels. And this is it. So this is our table. So X1 in the sequence is -2. X2 is 0. X3 is 2. 4, 6, 8. So those are the values that X can assume. The probability of each of those is 1/6. F of X is the cumulative probability as we, just add them up as you go. So it's the probability of being at that value or less, which means you add up the probabilities. So let's look at the probability of being strictly less than 5. So that means strictly less than 5. That means 4, 2, 0, or 1. So 1, 2, 3, 4. So it's going to be 4/6, which is 2/3. And notice we got 2/3. So let A be the event -2, 3, and 4. Now notice 3 is not even a possibility that X can assume. So the probability of that event is 0. So the probability that it's a -2 or 4 is 2/6, which is 1/3. And so this is how we would do it. We want X to be in the set A, so one of those, and then find the probability and sum it. We get 1/3. And the last is the probability that X is equal to 3. So, and it can't be 3, so it should be 0. So the probability that X is 3 is 0, which it should be. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.